So remember, we were here, and we realized that depending on the parameters, we will have either a fixed point or a stable limit cycle, right? Or something in between. And let's actually try doing this. So for example, if I take 0.06 for A and 0.6 for B, what do I get? Yes, stable limit cycle. Very good. So let's go to the codes. I think it was this one. Do I need to comment again everything? It's basically the same. Now I will just write down the places that we changed. Okay, this one we've changed. How glycolysis is written? Is this correct? Glycolysis equations. X corresponds to ADP, right? And again, glycolysis equations. Y corresponds to what? F6P. Very good. So now these ones are null-clines. Null-cline. And I'm plotting them too. This one in particular is x dot equals 0. I mean dx over dt equals 0, I believe. And this one is dy over dt equals 0. Can you follow, everyone? No. Null-cline means at that along that line there is no change in x. However, once you leave that line, you start changing x. In the same manner, this one is the other curve. Let's just plot these curves. I'm just choosing this portion and just plotting these ones. So do you see the familiar lines that you have seen in the book? You see the orbit. You can see that there is apparently a limit cycle here. Let's now run the whole system. Do you have any question before we run?
Those little blue arrows, they are created by the quiver.
Yes.
So we didn't create a figure or something. So I didn't understand how the function works.
Which function?
Quiver.
Quiver. Okay.
Yeah, it creates the arrows, but we didn't create any figure, so I didn't understand.
Okay. So what we do is we define dx1, which is remember x1 and x2 are matrices.
Okay, I understood them. So I understood that we also draw the vectors in corresponds to their magnitudes, but I didn't understand how the function works in like MATLAB.
Okay. Okay, let's do some examples. Quiver. Let's write 0, 0, 1, 1. Okay. What do you expect? Actually, this is wrong, right? Let's see what it produces. An arrow that starts at 0, 0 and ends. It's that easy? Very good. Very good. The lights are off, but luckily this one is connected to some higher order of power. So, then if I run this, now I run the whole thing. Actually, I will run it again. So I will start, for example, from here. What it biologically means? I have this much of ADP and this much of F7, F6P, right? Where do I go? To this limit cycle. Again, limit cycle is important for biological organisms because they are so robust, right? Like you may not find food for some time, but whenever you find the food, you eat it, maybe too much, less, I don't know, but everything settles to the normal cycle eventually. I mean, you get what I mean. So wherever you start, you end up in that limit cycle. Do you see? Yes? Yes.
You can also have some space, and where you click it, it will go to stable point instead of limit cycle.
There is no stable point here.
We showed like a line.
Exactly.
There was a stable.
Exactly. Let's do that. Let's do that. And I will do also that in a moment. I know what you are saying.
So it's two different parameters. If you change the parameters, one goes to limit cycle.
I will do something much better. Trust me. Do you trust me? Yes? Okay. So so let's go to somewhere here. Where should we go? 0.2 for B and 0.08 for A, for example. Okay? 0.2, 0.08, 0.08, 0.2. So now I have the fixed point, and you can see that there is a fixed point here because of the arrows. You already see it, right? So let's start somewhere. Do you see? You go to the fixed point. Wherever you start. So this is not an interesting organism. It always has the same amount of ADP and F6P, right?
Of the whole algorithm is expressed.
Yeah. So now let's also try something that we discussed during the break. What if I'm right at the top of this edge, right? What happens? Now I understand what happens. Actually, what happens is that limit cycle shrinks, and that is the point where limit cycle and stable fixed point are the same thing. Right? Do you understand my point? So this brings us to the subject of bifurcation. Let's see what is bifurcation. So you missed a lot. So here we will give a big pause, on the subject of limit cycles. We will start by dealing with bifurcations, and then we will go back and see what kind of bifurcation we had. Okay? First of all, what is bifurcation? Remember we had fixed points, etc., right? So bifurcations occur when you change some constant parameters in the nonlinear systems of equations, or just 1D flows, doesn't matter. For example, let's consider this one. Okay? If r is smaller than 0, what do you have? You have a plot that crosses the x dot equals 0 line twice, right? One of them is a stable point, the other one is unstable. Okay? And as you approach r equals 0, these points actually annihilate each other. It's just like electron-positron annihilation, right? It has nothing to do with that, but then some physicist watching this discovers that it has to do with that and gets Nobel Prize. Anyways, So do you understand this point? Do you see how relevant it is with our limit cycle becoming a stable fixed point when you have a certain range of parameters? No? And so this is called bifurcation, and I will show you another way of looking at it. Remember, we had, when r was smaller than 0, we had 2 points, right? And those points, as r approached 0, were approaching each other. So this is another way of drawing what is happening here, okay? This is the position of fixed point, position of fixed point, and this is the parameter. So what do you have? 2 points approaching, one unstable, one stable, and they give nothing. Here you have nothing actually, okay? So this kind of bifurcation is called saddle node bifurcation. Do you understand the word bifurcation? Bi is 2 and furcation is division. So this is not the only way this happens. There are many different kinds of bifurcations. For example, one of them is transcritical bifurcation, which is modeled by this equation. Let me remind you, it doesn't need to be this particular equation to have transcritical bifurcation. This is just for the sake of naming things, and they keep appearing over and over again, so they have some names. For example, over here, what happens if you are smaller than 0? You have unstable and stable node. The stable node is there until it is changed to an unstable one. So basically stable. Okay, so yes, okay. So you see the stable point over here? It stays there when r is smaller than 0. It stays at the origin, right? Then it becomes unstable after it passes after r becomes positive, right? What about here? What about the other point, this one? It's actually moving towards here and then becomes stable. So basically, if you are changing the parameter in this system, you can change, the equilibrium will stay the same as long as r is smaller than 0, and then it will change, the equilibrium will change to some other place as you go along. Do you understand my point?
But we need both those graphs to judge whether this becomes unstable and stable.
Yes.
Just by looking at x versus r, x versus parameter.
Yes.
Can I decide if this is unstable or stable?
Well, this plot, yeah, you plot after analyzing all these ones. This is like a summary of this one, because here in this plot, you plot only the fixed points, not all points on space, right? So let me give other examples. For example, supercritical pitchfork bifurcation, which is modeled by this equation, and where you have a stable node, stable fixed point, and then becomes unstable while producing 2 stable other points, okay? All these are different animals in the zoo of bifurcation. For example, this is subcritical pitchfork bifurcation, and you can even make it even more interesting by adding x to the 5. But you get what the bifurcation means, right? We will see that bifurcations are the route to chaos. Okay? But more about this later on. I will skip this part. So let's come back to our problem. What is happening here? here the story is a little bit different. Do you remember our equations? So now we have left bifurcation, we came back to our problem, original problem. We had limit cycle, and at certain parameter range it was going to a fixed point, right? So here notice that we have two parameters and we are in 2 dimensions. So there is much more fun to have, right? What happens here is that before, let's see this part. So these were just old friends from chapter 3, namely the saddle node, transcritical, and pitchfork bifurcation. Remember, we stayed in the real values of lambda, okay? They were just coalescing, coming together, going apart, etc. They never went to the imaginary axis. What happens here is that in the Hopf bifurcation, so-called Hopf bifurcation, the lambdas are actually going from some value in the real axis to their imaginary values. So, okay, what do you have if you are over here? Over here. A lambda that is real and negative. What do you have? Stable fixed point, right? Everything is attracted. What do you have if you have real negative, like minus, let's say 3.2, plus some, or plus minus some 1 times I or something like that? What do you have? Oscillation. Okay? So basically, what we are having here is supercritical Hopf bifurcation. Okay? Believe me or not. I hope I'm correct. Even if I'm not correct, I'm just a little bit incorrect. Okay? And besides, it's enough for me if you know that there is something called bifurcation, and it happens because we change parameters and you change the stability of the system. Okay? So, do I have anything else today? Okay, I will come to that, and I have a lot of time. So what I want to do now is to play around with the following. What if I write a code that has, while solving the system, varies, for example, let's say keep A at 0.1, okay, but take B from 0.6 all the way to 1 and then take it to 0.2. What do you expect to see? Okay, let me repeat myself. Let's say B is over here and A is over here. So what do you expect to get? Limit cycle, right? Let's keep revolving. What happens as you approach here? It becomes a fixed point. And how a limit cycle can become a fixed point? Shrinking down, right? So it will become a dot. Then if we go back from here, it will become again a limit cycle. Okay? So I happen to have a code for that. So let's say A is equal to 0.1 and B oscillates between it goes from 0.3 to 0.9. It oscillates in between, right? Are you with me? Ready? Now you have this limit cycle that shrinks down to a fixed point, then comes back, becomes a limit cycle. Then we go down from the other part, again a fixed point, and again a limit cycle in a moment. No? Yes. Do you see what's happening here? Yes?
It seems like there are two
Well, what do you mean by that? You mean like a fixed point that is over here and a fixed point over there? This is, again, I'm changing the parameter, so it's I'm comparing totally different systems with each other. Okay? Why I'm doing this? Because we will see in the next weeks that changing parameters, you can go from normal oscillations to like fixed points to limit cycles, and you can even go further to chaos, where you have strange attractors. But more about that later. So let's also, for example, fix B but change A. Okay, I fixed B, I changed A. So B is 0.6 and A is going between 0.05 and 0.13. So B is fixed and I'm going somewhere here, going back and forth. Okay. This one actually looks nicer because it goes to bigger limit cycle. Okay. Okay, very good. Then it will go again to the fixed point, etc. So basically, you can imagine that in 1D it was like one fixed point, then goes to 2, like this. This time it's one fixed point, but think in 3 dimensions, so it becomes something like this. So let me draw it actually. So something like this is happening. Do you understand my point? Yes, this is Hopf bifurcation.
So the proper definition of bifurcation is going from fixed point or to null or limit.
Yes, yes.
Does it have to be a limit cycle or could it be a spiral? Is that something else?
I don't know, but all these possible conditions, maybe not all of them, but they all have some names, as you mentioned. Yes. So let's. I wasn't expecting to have so much time for this final part, but then I even can read you some story. Okay. So, oscillating chemical reactions. Let me read. So, in the early 50s, there was this Russian biochemist, Boris Belousov. Okay. He was trying to create a test tube caricature of the Krebs cycle, a metabolic process that occurs in living cells. When he mixed citric acid and bromate ions in a solution of sulfuric acid and in the presence of a cerium catalyst, he observed to his astonishment that the mixture became yellow, then faded to colorless after about a minute, then returned to yellow a minute later, then became colorless again and continued to oscillate dozens of times before finally reaching equilibrium after about an hour. Okay? Back then, this was really amazing. you know a lot of chemistry. Have you ever seen anything like this?
Sort of.
You have, but it's modern chemistry, so now you can see them. But back then, today it comes as no surprise that chemical reactions can oscillate spontaneously. Such reactions have become a standard demonstration in chemistry classes, and you may have seen one yourself, right? But in Belousov's days, this discovery was so radical that he couldn't get his work published. It was thought that all solutions of chemical reagents must go monotonically to equilibrium. Do you know monotonically what it means? So if it decreases, it always decreases. If it increases, it always increases. That's what monotonical means. But here what we are seeing is that it goes to one thing, then goes back, then goes to one thing again, then goes back, until reaching the equilibrium. Yes, it reaches the equilibrium, but it oscillates before reaching. Okay? This is something totally new for chemistry. Okay. Belousov's paper was rejected by one journal after another, and even one editor added a remark that Belousov's supposedly discovered discovery is something like this. So they didn't believe him. It's a typical sad Russian story. Yeah, it didn't happen once. Yes. Well, I think both. I'm guessing both. But
I thought Soviets didn't share any scientific results with West.
well, it is 50. It is 50s.
Yeah.
Maybe not. But why I mentioned sad Russian story, because it's usually because of that reason. First of all, Russia and Russians have self-sufficient language and culture and everything. Like if they are just alone, they are enough to create amazing stuff. It's like there is West, there is Russia. I hope no one gets angry at me. So they created amazing stuff. They didn't share them. Then every once in a while, they rediscovered what West did, or West rediscovered what they did. But it is always a good meeting because you see one thing through totally different eyes. Okay? Your question was, do you have a question?
My question was no, like it was rejected from.
Maybe Russian, yes, journals, yes. Okay. Belousov managed to publish a brief abstract in the obscure proceedings of Russian medical meeting. Okay, although his colleagues weren't aware of it until years later. Nevertheless, word of this amazing reaction circulated among Moscow chemists in the late 50s, and in 1961, a graduate student named Zhabotinsky was assigned by his advisor to look into it. Zhabotinsky confirmed that Belousov was right all along and brought his work to light at an international conference in Prague in 1968, one of the few times that Western and Soviet scientists were allowed to meet. That's the answer to your question also. Well, nowadays we know this reactions as Belousov-Zhabotinsky reaction, right? Okay, let's look at the reaction one more time. Basically, again, X and Y corresponds to something chemical, some chemicals. And the thing is that this one is very, very similar to the one that we have analyzed. Okay. And you will find, again, stable fixed points, stable limit cycle. Do I have? No. Do I have it here? I don't think so. Well, again, you will have a Hopf bifurcation. we will come to this reaction is also interesting because if you add the spatial terms, like where these reactions are actually taking place, then we will see that they are forming spirals, etc. We will come to those kind of stuff later on. So maybe it was short, but let's stop here. Do you want to stop here, or do you want to see more?
It's a trap question.
Okay, let me think. Okay, at least let me show you what is coming next. What is coming next is that we will start looking at, well, this is our Poincaré. By now you all like him. We will look at the amazing discoveries of Robert May. He's still alive. And you can see that he is, I mean, nature, 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 nature. Nature, science, science, nature. Okay. We will look at a couple of them. Not a couple of them. I think we will look at this particular paper. Then we will look at Lawrence's work at MIT. We will get familiar with strange attractors, the butterfly effect, etc. Then we will look at Mitchell-Feigenbaum's discovery. And all of them are those things that you can do by playing in your computer, and it really changed the way we see the world philosophically and in every way. Thank you very much. Let's see you next week.